For 5.4, analyzing graphs and polynomial functions. Your new vocabulary is location principal, relative maximum, relative minimum, extrema, and turning points. Okay, so think of the location principal as you're locating zeros. If you had a table of values, say it's x and y, and you're going from -1, 0, 1, 2, so on and so forth. What you want to look at is your y values. Say this is 2, 1, and then 0. No, let's not do 0. That's going to mess you up. Let's say it jumps to -1, and then this is like -5. What you're looking for is where you have a change in sign, and you can tell that that's where your 0 is going to be between those two x values. Okay, so what you're looking for is a change in sign, and that's how you're locating your zeros, or what's your x values you're looking for. Alright, so make sure you have that copied down because I'm about to erase it. Alright, next one is a relative maximum. Alright, so if we're looking at a graph, we're looking for a maximum point, and we're only looking between a certain x values, because if you looked at the entire graph on the entire real number line, there really is no maximum value, because this goes on and on and on forever to infinity. And so why we shorten the scope is so that way we can look at relative max and mins. So whatever looks like the top of a hill, that's going to be your relative max. And whatever looks like the bottom of a valley, that's going to be a local min, or a relative min. Now, extrema are just the points that are relative max and mins. So that's just a fancy name for a max or a minimum, is extrema. And usually your max or mins are called turning points, because if we follow our graph, you see how we're descending, and then all of a sudden now we're going to go up. Well, we turned at this relative minimum, and now we're going up and we're following our curve, and then we're going to turn again and go downwards again. So these are also called turning points. So we have relative max, relative min, extrema, and turning points pretty much mean the same thing. Alright, so example number 1, it says graph f of x is equal to -x cubed minus 4x squared plus 5 by making a table of values. Well, what I want you to do is I want you to go on your calculator and actually plug this in like you see it. Do not include the f of x equals. That will mess up your graph. Now, you should get a graph that looks like this on your calculator. If you don't, you need to ask one of your teachers what happened. The next thing I want you to do is to pull up a table on your calculator. And the way you do that is you press your menu button, you go to number 7, table, and you'll go to number 1 that says split screen table. Alright, so if you take a look at your graph, we're only really looking at a few numbers here on your x. If you were to graph this, I would say, okay, I would look at, let's see, what is that, 1, 2, 3, 4, x is -4, -3, -2, -1, 0, and 1. So if you did actually have to make a table of values, these x values will give you a pretty good indication of what you need. -4, -3, -2, -1, 0, and 1. And if you look at your graphing calculator, you get these values of 5, -4, -3, 2, 5, and 0. Now, to bring it back to the location principle, had you been given a table of values and you needed to find where it crossed the x-axis, you would look at your y values and you would look for a sign change. So I have a sign change between 5 and -4. I have another sign change between -3 and 2. And anytime I have a y value of 0, that means it crossed the x-axis. So if we weren't given our graph, we would still be able to find what numbers between, or what x values between my roots are. So we have a root between -4 and -3, between -2 and -1, and then we have one at the point 1, 0. And you can also verify this on your graph. Now, I've already talked about the location principle, but here's what it has in your book. You're more than welcome to write it down, but if you feel like you have it, don't worry about it. Example number 2, we're going to determine consecutive values of x between which real 0 of the function f of x equals x to the 4th minus x cubed minus 4x squared plus 1 is located. Then we're going to draw the graph. Alright, well, since we are in the technology age, I want you to go ahead and graph this in your calculator so you can see what it looks like. And you should get a function that looks like the one below. If you don't, then something was probably put in your calculator incorrectly. The next thing I want you to do is to go to your table. Remember, you go to Menu 7, 1, and it should pop up your table of values. Make sure you cleared out your other function before by pressing Dock B. If you take a look at your graph, we're only looking at a couple of x values that are pretty important. So I would say the x values from here to here are pretty important, and that's what we're going to focus on in our table of values. So we have x and y, and if I look at my graph, I go from -3, -2, -1, 0, 1, 2, 3, let's see, 1, 2, 3, 4. We're not going to go 4. There we go. Alright, so looking at my graph, I have the following y values: 73, 9, -1, 1, -3, -7, and looks like 19. As you can tell from the graph, we have 1, 2, 3, 4 real roots. And if we were using the location principle, you would look for a sign change in your y values. We have a sign change here, here, here. Oh, I missed one. Right there. So there's our 4 sign changes. So we would say that we have roots between -2 and -1, between -1 and 0, between 0 and 1, and between 2 and 3. So if you were to actually write your answer out, I have that written for you at the bottom of this page, right here. Example number 3, it says graph f of x equals x cubed minus 3x squared plus 5, and estimate the x coordinates at which the relative maxima and relative minima occur. Alright, so the first thing you need to do is plug this into your calculator. Remember, all you're doing is plugging in the x cubed minus 3x squared plus 5. Make sure to clear out anything you had before by using Dock B. You should get a graph that looks like this. If you don't, then something's wrong. Now, remember, relative maximum is like the top of a hill. So here we have a top of a hill. So that's going to be a relative max. And the bottom of a valley, oh my gosh, I can't speak today. The bottom of a valley is going to be a relative min. And now our question is asking for the x coordinates at which these occur. So what you can do is you can actually look at your table. And what I'm looking at is when you don't have something that's on a pretty point, this would be good for if, say, your relative max or min were between two integers. This is what this procedure would be good for. I'm just going to look at x values that are between -3 and 1, 2, 3. So -3 and 4 on my table. And what I have is -49. Oops, sorry about that. To spare you, I went ahead and wrote out all the y values. Alright, so what you're looking for is around here, around this x value of 0. If we look at our y value, you see how the 5 on either side is bigger than 1 or 3. So that means that our graph actually turned directions between -1 and 1. And we know that x equals 0 is where we actually have a relative max. And also, let's see, at this point right here, we went from a bigger number to a smaller number to a bigger number again. That means we have a relative min. So that was a max, this was a min. So at x equals 2, we have our relative min, and the way we would write our answer is at x equals 0, there's a relative max, and x equals 2, there's a relative min. Alright, for our last example, this is the weight W in pounds of a patient during a 7-week illness as modeled by the function W of n. Oh, just kidding. You're going to have more noises in this video. Let's see, so we have our function here where n is the number of weeks since the patient became ill, and we need to graph the equation. So again, go into your calculator, doc B to clear it, and plug in just this piece, not the W of n, or else you're going to get an error. Now, one thing you don't have to put n. You can, but really we can just change it to an x in your calculator. Now, you should get a graph that looks like this. Some of you might think, oh no, my graph didn't appear. And the reason being is if you look at your calculator, it only goes from -10 to 10 and from -7.39 to +7.39. We're talking about we need the weight is 110. So on the y-axis, we need at least to go up from 0 to, let's say, 150. And you can fix this in your window. You go to Menu, number 4, which is called Window Zoom. And you're going to go to Window Settings. Here it's asking for your X-min, your X-max, your scale. We'll keep it at auto. Y-min and Y-max. Alright, I want you to plug in the following. Now on this, you might have to play around with it a little bit to make sure it actually looks right. But when I played around with it, this is what got us the same graph over here. Now on B, we're going to describe the turning points on the graph and its end behavior. Well, we know that we have the bottom of a valley here. That's a relative min. And we also know that's going to be a turning point. So we have a turning point and a relative min at x equals 4. Now to describe the end behavior, let's look. We have as n is approaching infinity, my function is actually approaching infinity as well. So as n approaches infinity, no, not f of x, excuse me. Let's see, W of n approaches infinity as well. Now, let's think about this. Can we have negative time? That would be no. Can we have negative weight? No. That's why we don't worry about anything else but the first quadrant, and that's why we're only going to n is infinity rather than going to negative infinity like we do on all the other graphs. C, it says, what trends in the patient's weight does the graph suggest? Well, if we look at our x-axis, we see that the patient's weight is decreasing in the first 4 weeks, and after the first 4 weeks, they begin gaining weight again. So, in words, the patient lost weight the first 4 weeks, then gained weight afterwards. And our last question, it says, is it reasonable to assume the trend will continue indefinitely? When you have a question like this, you always want to think back to the problem. What exactly are we talking about? We're talking about weight. Now, I know you've seen those TV shows where you have people that are like 700 pounds, but you never actually reach infinity pounds. So this might continue for a few weeks, but it's not going to continue indefinitely. Thanks for watching. Have a great day.